This tutorial is for 5th grade, Module 3, Lesson 2. In this lesson, we're going to use the number line to add fractions with like denominators. The first question is 2/5 plus 1/5. I'm going to start by dividing my number line into fifths. I'll start by showing 0 and 1/2. And I'll divide this number line into 5 pieces to show the fifths. I'm just going to estimate here. And I'm going to label each piece. So 0 would be the same as 0/5. Then I have 1/5, 2/5, 3/5, 4/5, and 5/5. My first fraction is where I'm going to start on the number line. I'm going to start on 2/5, and I'm going to jump 1/5 more. So that just means I'm going to do a hop, and the hop itself is worth 1/5. When I do that, I land on 3/5. So 2/5 plus 1/5 is 3/5. When we use the number line for this type of addition, the students are not tempted to add their denominators. A common misconception in the past. Here they see that it wouldn't make sense to add your denominators because if you're hopping 1/5, you simply just jump on 3/5. So again, that explains why 3/5 is our answer and why 3/10 would not make sense. This problem takes it a little bit further. This problem asks us to show 2 times 3/4 and then plus 1/4 on the number line. Well, I have to do some estimating here before I make my number line. 3/4 is just shy of 1/2. That tells me that my answer is probably going to be more than 1/2 since I'm taking 2 times that number and then adding a 4th. Instead of starting with 0 at one end and 1 at the other end, I'm going to put 2 at the other end because I feel that the answer is definitely going to be more than 1/2. The halfway point then is my 1/2 spot. Now I'm going to divide each of these sections into fourths. So from 0 to 1 I have fourths, and from 1 to 2 I have 4 pieces. I'll mark those pieces 0/4, 1/4, 2/4. You can see once I've passed the 1/2 part, my fractions become improper fractions. 5 is greater than 4, but that makes sense. If it takes 4/4 to make a whole, and I'm past 1/2, you can see why I have more than 4/4. So I'm going to represent these using the improper fraction version. So I have 5/4, 6/4, 7/4, and 8/4. I can also write that down below as a mixed number, but I don't have to. Sometimes it helps the students, though, to see that this point is 1/2 and 1 more 4th. Here I would have 1/2 and 2/4, 1/2 and 3/4, 1/2 and 4/4. Again, this part isn't necessary unless the student is having trouble understanding that once you pass that 1/2 portion, you do have what amounts to a mixed number. Okay, so now we have to take 2 times 3/4. I'm going to look at that as 2 hops of 3/4. Here's my first hop. So I've done a hop of 3/4. 1/4, 2/4, 3/4. I need to do that again because I need 2 hops of 3/4. So I'm going to do another hop of 3/4. Here's another representation of that, so I've hopped 3 more sections. That puts me at 6/4. I still have to add the 1/4 to finish out my problem. So from here, I hop 1/4. So I've done my 2 jumps of 3/4 and my 1 hop of 1/4, and that puts me at 7/4 or 1 3/4. The students can write their answer either way. The improper fraction is fine. If they want to write it as a mixed numeral, that's fine too. So this shows how we can use multiplication of fractions and addition on the number line. In the next section, we're going to show how multiplication is related to repeated addition. Back in 3rd grade, when the students learned their multiplication facts, they started by looking at multiplication as repeated addition. That was with whole numbers. Same process when we're talking about fractions. Here it says, express each fraction as the sum of 2 or 3 fractional parts, the sum being the answer to an addition problem. Then we're going to rewrite each as a multiplication equation. If I start with 6/7, I see I have a couple of ways I can attack this problem. I know that I could write 6/7 as 2/7 plus 2/7 plus 2/7. So that's the sum of 3 fractional parts. Or a student could write it as 3/7 plus 3/7. That would be the sum of 2 fractional parts. Either answer is correct. 2/7 plus 2/7 plus 2/7 equals 6/7. 3/7 plus 3/7 also equals 6/7. To show these as multiplication problems, if I want to show this addition problem as a multiplication problem, I would say that I'm taking 3 times 2/7. I have 3 groups of 2/7. If I want to show this problem as a multiplication problem, I would say 2 times 3/7. I have 2 groups of 3/7. Either answer is correct. Here I have 9 halves. I can represent 9 halves as 3 halves plus 3 halves plus 3 halves. To represent that as a multiplication problem, I would say I'm taking 3 times 3 halves. 3 groups of 3 halves gives me 9 halves. I could also represent it this way. I could say that I have 4 halves plus 4 halves plus 1 half. So that's going to change my multiplication sentence a little bit. This tells me that I'm taking 2 times 4 halves plus the 1 half at the end. A little more complicated to do it this way, but again, that answer would be correct. In my final section, I'm going to use number bonds to express each of the following as the sum of a whole number and a fraction. You'll see that all of these fractions are improper fractions. The numerator is greater than the denominator. That tells me that I have more than one whole in each of these fractions. So if I look at my first one, 9/7, since 7 is the denominator, that tells me that it takes 7/7 to make one whole. So I'm going to write that as a number bond. 9/7 is the same thing as 7/7 and 2/7. To write this as a whole number and a fraction, then 7/7 is equal to 1 whole, and then I have 2/7 left over. 9/7 is equal to 1 whole and 2/7. Looking at 3 halves, since 2 is my denominator, I know it takes 2 pieces out of the 2 to make 1 whole. I started with 3 halves. Since I've used 2 halves here, I have 1 half left over. The 2 halves is the same as 1 whole, and I still have 1 half left over. 3 halves is the same as 1 whole and 1 half. Down here I'm working with sevenths again. 7/7 is the same as 1 whole. Since I started with 12/7, I have 5/7 left. 7/7 and 5/7 is the same as 12/7. 7/7 equals 1 whole, and I have 5/7 left. 12/7 is equal to 1 whole and 5/7. And finally, I have 15/9. Since 9 is my denominator, I know that it takes 9 pieces out of 9 to make 1 whole. I started with 15 pieces. That gives me 6 pieces left. 9/9 plus 6/9 is the same as 15/9. I'll take the 9/9 and turn that into one whole, and I'll show that I still have 6/9 left over. 15/9 is equal to 1 and 6/9.